My name is Shai Williams, and today we're going to talk about an independent samples factorial ANOVA. And specifically, we're going to do a 2x2 ANOVA. So we're going to have 4 different groups. Let's start off by making some data, and we're going to use a cbind function, but before we populate that, let's do it one at a time. So I want to make 4 different distributions, so I'm going to do that with the rnorm function. First is going to have 50 data points, then we're going to have a mean of 20, standard deviation of 4, then we'll make our second distribution, which is the same, but with a mean of 25. And then we have a third distribution, which is the same, but a mean of 30. Then finally, we have our fourth distribution with a mean of 35. So what that looks like is essentially, we have 200 data points, where the first 50 is our first distribution, second 50 is our second distribution, and so forth. So next what we need to do is designate our levels of our factors. So the next column is going to be our first factor, and it's going to have 2 levels. The column after that's going to be our second factor, and it's going to have 2 different levels as well. So what I'm going to do is I'm going to just write it out here, and then you'll see what I do in a second here. So we're going to use the repeat function. So we're going to do 1 to 2 100 times, but then we're going to sort it. So we're going to get 100 ones and 100 twos. And that looks like this. Great. I'm going to put that up here. Our second level is going to be a little bit complicated, but what we're going to do is 1 to 2, 50 times, and we're going to sort that. So we just did the same thing, but we're going to do 50 at a time. And then we're actually going to repeat this whole thing twice. It's a little complicated, but you'll see what I mean in a second. That gives us this basic. So then we get 1 for 50, then 2 for 50, then 1 for 50, and then 2 for 50 again. And let's look at that here. So what we see, these are our scores. This is the level identifier of our first factor, and this is the level identifier of our second factor. So the first group is identified as 1, 1. The second group is going to be 1, 2. The third group is going to be 2, 1. And then the fourth group is going to be 2, 2. Now, finally, we also need to add our participant IDs in here as well, but since we have 200 independent samples, what we could just do is go 1 to 200, and that's our ID. That looks finally like this. So those are our 200 people. Now this is about the time that I say let's plot our data, but really it's a complex design and it's hard to do with native R functions. So I'll leave that for another video where I use ggplot2, which is much better at handling these complex designs. So next we need to prepare our data. We do this by first changing it to a data frame as .data.frame, and that turns it into this where we can look at our 4 variables. Let's name those columns as, let's go, scores levels 1, which is our factor 1, levels 2, which is our factor 2, and then finally we have our subject IDs, and that's great, and that's what we get here, but we actually have 2 levels and subjects, and these are actual factors, not numeric values. So let's change that here. So we want to change our first factor into a factor. And we'll do that for all of these here, except for the first one, which is our scores, which is actually numeric. And what we get is our first one's numeric, and then we have 3 different factor columns. We're going to use the easy package to do an easy ANOVA. And the way that this works is we're going to go ANOVA underscore results equals easy ANOVA. It's not too intuitive, but it is fairly easy to use. So we have dv, which is our dependent variable parameter, but it has this equals dot brackets, and we're going to put our scores here. And the scores is this column name here. Then next what we want is our between subject variable. And so if we were doing a repeated measures design, this would actually be within. And then we're going to put our levels 1, comma, levels 2. Then finally what we need is our WID, which is our subject identifiers. We want to have a detailed report, so we're going to put detailed equals true. We want to use sums squared type 3, which if you don't know what that is, then look it up, it's pretty important. Then we finally are going to tell it what data frame we're looking at. So data, I should probably rename this better, but data is our variable here. Now, what we get are our results here. So the first thing you'll see is it gives us our homogeneity of variance assumption check with the Levene's test, which is pretty cool. And we see that there is no violation of this assumption. So great, we can move on. Then what we have here is an intercept, but ignore that. We have our first factor, our second factor, and then our interaction. So this is our main effect 1, main effect 2, and our interaction effect. We have degrees of freedom of our numerator, of our denominator, we have sums of squareds, we have our f values, we have our p values, and then we have our generalized eta squared. So if we go through this, our degrees of freedom makes sense because they're 1, because we have 2 levels in each condition. So k is 2 minus 1 is our degrees of freedom. And then we have our degrees of freedom of numerator of 196 because that's our total n minus our total number of levels. So we have 2 factors with 2 levels, which is 4 levels. So our 200 people minus 4. And so for our first main effect, we have this f value. And so when we look at our p-values, we see our first main effect's very small, so it is significant. Same with our second main effect, but our interaction effect isn't significant. So how do we write this out? So we're going to put f 1 comma 196, which is our 2 degrees of freedom, equals our first f value, which is 386.86. Oops. And our p value is less than 0.0001, and our generalized eta squared is 0.66. So usually generalized eta squared has the eta symbol in it, but I don't want to bother trying to put that into R. So when you report it in a manuscript or whatnot, make sure you're using the right symbols. So we could do this for, that's our first main effect, our second main effect, and then our third. So the degrees of freedom is consistent across all of them, but our second main effect has an f value of 99.06 and a p-value that's also very small, so less than 0.0001. And then our generalized eta squared is 0.34. And then finally, what we see in our interaction effect is a f value of 0.15, or 16, I should say, a p-value of 69 or 0.6905, and a generalized eta squared of 0.00. And there you have it.